Gauss's law is one of the four Maxwell's equations that form the foundation of classical electrodynamics. It relates the electric flux through a closed surface to the charge enclosed by that surface. Mathematically, it is expressed as contour integral SEdA equals 0 kenk, where \oint_s denotes a surface integral over a closed surface, S. \math E is the electric field. D\math A is a vector representing an infinitesimal area on the surface, S, pointing outward. Q_\text inc is the total charge enclosed within the surface, S. \epsilon_0 is the permittivity of free space. 2. Electric flux. Electric flux \phi_e through a surface is a measure of the number of electric field lines passing through that surface. For a uniform electric field, \math E passing through a flat surface of area, perpendicular to the field, the electric flux is given by E equals EA equals ECAS, where \theta is the angle between the electric field and the normal to the surface. For a closed surface, the total electric flux is the sum of the flux through each infinitesimal area element, D\math A. 3. Gaussian surface. A Gaussian surface is an imaginary closed surface used in the application of Gauss's law. The choice of Gaussian surface is crucial and is often dictated by symmetry considerations. Common examples include spherical symmetry, 4-point charges or spherically symmetric charge distributions; cylindrical symmetry, for infinitely long line charges; planar symmetry, for infinite plane sheets of charge. For applications of Gauss's law, Gauss's law is particularly useful in calculating electric fields for charge distributions with high symmetry. Here are a few examples. Point charge. For a point charge, Q, the electric field at a distance, r, from the charge is given by Coulomb's law. Using a spherical Gaussian surface of radius, r, Gauss's law simplifies to E4R2 equals 0 QE equals 40R2Q infinite line charge. For an infinitely long line charge with linear charge density \lambda, using a cylindrical Gaussian surface of radius, r, and length, l, Gauss's law gives E2RL equals 0 LE equals 20R infinite plane sheet of charge. For an infinite plane sheet with surface charge density \sigma, using a cylindrical Gaussian surface that intersects the plane, Gauss's law yields E2A equals 0 AE equals 205. Differential form of Gauss's law. Gauss's law can also be expressed in differential form using the divergence theorem. The differential form states that the divergence of the electric field \math E at any point is proportional to the local charge density \rho at that point. E equals 0. This form is particularly useful in solving problems involving continuous charge distributions. 6. Historical context. Gauss's law is named after Carl Friedrich Gauss, who formulated it in 1835. However, it was first formulated by Joseph Louis Lagrange in 1773 in the context of gravitational fields. Gauss's law is a cornerstone of electromagnetism and is essential for understanding electric fields and charge distributions. 7. Relation to other laws. Gauss's law is closely related to Coulomb's law. In fact, Coulomb's law can be derived from Gauss's law and vice versa. Gauss's law also has analogues in other fields of physics, such as Gauss's law for magnetism and Gauss's law for gravity, both of which follow an inverse square law similar to the electric case. Permittivity, denoted as \epsilon_0, the permittivity of free space, plays a crucial role in Gauss's law and in the broader context of electromagnetism. 1. Definition of permittivity. Permittivity is a measure of how much electric field, E, is permitted or allowed to pass through a material. In the context of free space, vacuum, the permittivity is denoted as \epsilon_0 and has a value of approximately 8.854 times 10 caret -12 \text f/m farads per meter. 2. Role in Gauss's law. In Gauss's law, permittivity appears in the denominator of the equation, contour integral SEdA equals 0 kenk. This indicates that the electric flux through a closed surface is directly proportional to the enclosed charge and inversely proportional to the permittivity of free space. Essentially, \epsilon_0 acts as a scaling factor that determines the strength of the electric field generated by a given charge. 3. Physical interpretation. Permittivity reflects how much resistance is encountered when forming an electric field in a medium. A higher permittivity means that the medium can store more electric field energy for a given amount of charge. In free space, \epsilon_0 sets the baseline for this property. 4. Relation to Coulomb's law. Permitivity is also fundamental in Coulomb's law, which describes the force between two-point charges, F equals 401 R2 Q1 Q2. Here, epsilon_0 determines the magnitude of the electrostatic force between charges. A lower permittivity would result in a stronger force for the same charges and distance. 5. Permittivity in materials. In materials other than free space, the permittivity is denoted as epsilon and is typically greater than epsilon_0. The relative permittivity, or dielectric constant, kappa, of a material is defined as kappa equals 0. This factor, kappa, indicates how much more the material can permit electric field lines compared to free space. Materials with high permittivity are used in capacitors to increase their capacitance. 6. An impact on electric field and potential. Permittivity affects the electric field, math, E, and electric potential, V, in a medium. For a given charge distribution, a higher permittivity reduces the electric field strength and modifies the potential distribution. This is crucial in designing electronic components and understanding the behavior of electric fields in different media. 7. Historical and practical significance. The concept of permittivity was developed as part of the broader understanding of electromagnetism in the 19th century. It is essential in the design of capacitors, insulators, and other electronic components. Understanding permittivity helps in predicting how materials will respond to electric fields, which is vital in many technological applications. In summary, permittivity is a fundamental property that influences how electric fields interact with materials. In Gauss's law, it serves as a key factor that relates the electric flux through a surface to the enclosed charge, thereby shaping our understanding of electric fields and their behavior in different environments. Wave speed. The speed of electromagnetic waves in a medium is determined by both the permittivity, epsilon, and the permeability, μ, of the medium. The wave speed, v, is given by v equals 1. In free space, the permittivity is epsilon_0, and the permeability is μ_0, leading to the speed of light, c equals 001. In a material medium, the permittivity, epsilon, is typically greater than epsilon_0, which reduces the wave speed compared to the speed of light in a vacuum. 2. Wavelength and frequency. For a given frequency, f, the wavelength, λ, of the wave in a medium is related to the wave speed, v, by λ equals fv. Since the wave speed, v, decreases in a medium with higher permittivity, the wavelength, λ, also decreases. This means that electromagnetic waves have shorter wavelengths in materials with higher permittivity. 3. Refractive index. The refractive index, n, of a medium is defined as the ratio of the speed of light in a vacuum to the speed of light in the medium. N equals Vc equals 00. For non-magnetic materials, where \mu\approx \mu_0, the refractive index simplifies to n almost equal to 0. A higher permittivity results in a higher refractive index, which affects how light bends when entering the medium from another medium, Snell's law. 4. Impedance of the medium. The intrinsic impedance, eta, of a medium is given by eta equals. In free space, this is \eta_0 equals \sqrt \frac \mu_0 \epsilon_0. In a material medium, the impedance changes with permittivity. A higher permittivity lowers the impedance, affecting how waves are transmitted and reflected at boundaries between different media. 5. Attenuation and absorption. In lossy materials, permittivity can be complex, with the imaginary part representing the material's ability to absorb electromagnetic energy. The complex permittivity, epsilon equals epsilon j epsilon, leads to attenuation of the wave as it propagates through the medium. The attenuation constant, alpha, is related to the imaginary part of the permittivity. Proportionality. Higher epsilon means greater energy loss and stronger attenuation of the wave. 6. Phase velocity and group velocity. Permittivity affects both the phase velocity, the speed at which the phase of the wave propagates, and the group velocity, the speed at which the energy or information travels. In dispersive media, where permittivity varies with frequency, these velocities can differ, leading to phenomena like dispersion, where different frequency components of a wave packet travel at different speeds. 7. Practical applications. Understanding permittivity is crucial in designing and analyzing various devices and systems, such as antennas. The design of antennas depends on the permittivity of the surrounding medium. Waveguides. The propagation of waves in waveguides is influenced by the permittivity of the material filling the waveguide. Optical fibers. The core and cladding of optical fibers have different permittivities to ensure total internal reflection and efficient light transmission. Radar and communication systems. Permittivity affects signal propagation, reflection, and absorption, impacting the performance of these systems. In summary, permittivity is a fundamental property that affects the speed, wavelength, refractive index, impedance, attenuation, and dispersion of electromagnetic waves. Its influence is critical in both theoretical studies and practical applications of wave propagation. When electromagnetic waves encounter an interface between two media with different permittivities, several phenomena can occur, including reflection, refraction, and transmission. Here's a detailed explanation of these effects. 1. Reflection and transmission. When an electromagnetic wave hits the boundary between two media, part of the wave is reflected back into the first medium, and part of it is transmitted into the second medium. The reflection and transmission coefficients depend on the permittivities epsilon_1 and epsilon_2 of the two media. Reflection coefficient R. This describes the ratio of the reflected wave's amplitude to the incident wave's amplitude. It is given by R equals Z2 plus Z1 Z2 Z12, where Z_1 and Z_2 are the impedances of the two media, which depend on their permittivities and permeabilities. Transmission coefficient T. This describes the ratio of the transmitted wave's amplitude to the incident wave's amplitude. It is given by T equals Z2 plus Z12 Z22 2. Snell's law and refraction. The change in wave direction when it passes from one medium to another is described by Snell's law. N1 sin 1 equals N2 sin 2. Where N_1 and N_2 are the refractive indices of the first and second media, respectively, and \theta_1 and \theta_2 are the angles of incidence and refraction. The refractive index N is related to the permittivity by N equals 0. 3. Impedance matching. The impedance of a medium is given by Z equals. When the impedances of the two media are matched, Z_1 equals Z_2, there is no reflection, and all the wave energy is transmitted into the second medium. This is crucial in designing antireflective coatings and other optical devices. 4. Brewster's angle. At a specific angle of incidence, known as Brewster's angle, the reflected wave is completely polarized perpendicular to the plane of incidence. Brewster's angle \theta_b is given by B equals tan 1 n1 n2. At this angle, the reflection coefficient for the parallel component of the electric field becomes 0. 5. Total internal reflection. When a wave travels from a medium with higher permittivity to one with lower permittivity, and the angle of incidence exceeds a critical angle \theta_c, total internal reflection occurs. The critical angle is given by C equals sin 1 n1 n2. Beyond this angle, the wave is completely reflected back into the first medium, and no transmission occurs. 6. Surface waves. At the interface between two media with different permittivities, surface waves can also be generated. These waves are confined to the vicinity of the interface and decay exponentially away from it. Surface plasmon polaritons are a common example, occurring at the interface between a metal and a dielectric 12. 7. Practical applications. Understanding these phenomena is essential in various applications, such as optical fibers. Total internal reflection is used to confine light within the core of the fiber. Antennas. Impedance matching is crucial for efficient transmission and reception of signals. Lenses and prisms. Refraction principles are used to design lenses and prisms for focusing and directing light. In summary, the interaction of electromagnetic waves with an interface between two media with different permittivities involves complex behaviors like reflection, transmission, refraction, and the generation of surface waves. These effects are governed by the properties of the media and the angles of incidence, and they have significant practical implications in various fields of science and technology. Electromagnetic waves can be polarized in different ways. Linear polarization. The electric field oscillates in a single plane. Circular polarization. The electric field rotates in a circular motion as the wave propagates. Elliptical polarization. A general form where the electric field describes an ellipse. 2. Reflection and transmission coefficients. The reflection and transmission of waves at an interface depend on the polarization of the incident wave. For linear polarization, the behavior differs based on whether the electric field is parallel p-polarized or perpendicular s-polarized to the plane of incidence. S-polarization, perpendicular. The electric field is perpendicular to the plane of incidence. The reflection coefficient R_s and transmission coefficient T_s are calculated differently compared to p-polarization. P-polarization, parallel. The electric field is parallel to the plane of incidence. The reflection coefficient, R_P, and transmission coefficient, T_P, are influenced by the angle of incidence and the permittivities of the media. 3. Brewster's angle. For p-polarized light, there exists a specific angle of incidence, known as Brewster's angle, at which no reflection occurs. At this angle, the reflected and refracted waves are perpendicular to each other. Brewster's angle \θ_b is given by B equals tan 1 n1 n2, where n_1 and n_2 are the refractive indices of the two media. At Brewster's angle, the reflection coefficient for p-polarized light becomes 0. For total internal reflection and polarization, when light travels from a medium with higher refractive index to one with lower refractive index, and the angle of incidence exceeds the critical angle, total internal reflection occurs. The polarization of the incident wave affects the phase shift upon reflection. For S-polarized and P-polarized waves, the phase shifts differ, leading to changes in the polarization state of the reflected wave. 5. Anisotropic media. In anisotropic media, the refractive index depends on the polarization and direction of propagation of the wave. This leads to phenomena such as birefringence, where a single incident wave splits into two waves with orthogonal polarizations, each traveling at different speeds. 6. Practical applications. Understanding polarization effects at interfaces is crucial in various applications. Optical coatings, antireflective coatings are designed considering the polarization of light to minimize reflect ions. Polarizing filters used in photography and displays to control the polarization state of light. Fiber optics, polarization maintaining fibers are used to preserve the polarization state of light over long distances. Radar and communication systems, polarization is used to reduce interference and improve signal clarity. 7. Boundary conditions. At the interface, the boundary conditions for the electric and magnetic fields must be satisfied. These conditions ensure the continuity of the tangential components of the electric and magnetic fields across the interface. The specific boundary conditions depend on the polarization of the incident wave and the properties of the media. 12. In summary, polarization plays a critical role in determining how electromagnetic waves interact with interfaces. It affects reflection, transmission, refraction, and the overall behavior of waves in various media. Understanding these effects is essential for designing optical devices and systems that rely on precise control of light. Birefringence, also known as double refraction, occurs in anisotropic materials where the refractive index varies with the direction of light propagation. This phenomenon significantly affects how light behaves when passing through certain crystals. Here's a detailed explanation. 1. Basic principle of birefringence. Birefringence happens because anisotropic crystals have different refractive indices along different crystallographic axes. When light enters such a crystal, it splits into two rays, ordinary ray, O-ray. This ray follows Snell's law and experiences a constant refractive index regardless of the direction. Extraordinary ray, E-ray. This ray experiences a refractive index that varies with the direction of propagation within the crystal. 2. Double refraction. As a result of birefringence, the incident light beam splits into two polarized rays that travel at different speeds and take different paths through the crystal. This can be observed in crystals like calcite, where placing the crystal over text results in seeing double images of the text. 3. Optical axis. The optical axis of a birefringent crystal is the direction along which there is no birefringence, meaning the refractive indices for both rays are the same. When light travels along this axis, it does not split into two rays. 4. Phase retardation. The difference in speeds between the ordinary and extraordinary rays causes a phase difference, or retardation, between them. This phase retardation can lead to various interference effects, which are useful in applications like waveplates and polarizing filters. 5. Applications of birefringence. Birefringence is exploited in many optical devices and scientific techniques. Waveplates, used to alter the polarization state of light. A quarter wave plate, for example, can convert linearly polarized light into circularly polarized light. Polarizing microscopes, used to study stress patterns in transparent materials and to identify minerals. Liquid crystal displays, LCDs utilize the birefringent properties of liquid crystals to control light transmission and create images. 6. Examples of birefringent materials. Common birefringent materials include calcite, exhibits strong birefringence and is often used in optical instruments. Quartz, widely used in waveplates and optical devices. Mica, used in polarizing microscopes and as a dielectric material in capacitors. 7. Mathematical description. The birefringence \delta n is defined as the difference between the refractive indices of the extraordinary and ordinary rays. N equals Ne no, where n_e is the refractive index of the extraordinary ray and n_o is the refractive index of the ordinary ray. 8. Visualization and practical effects. When light passes through a birefringent crystal, the two rays can interfere with each other, creating colorful patterns known as interference colors. These patterns are used in stress analysis and material science to study the internal structure and properties of materials. 12. In summary, birefringence causes light to split into two rays with different polarizations and speeds, leading to various optical effects and practical applications. Understanding this phenomenon is crucial in fields ranging from mineralogy to advanced optical engineering. A quarter wave plate is an optical device used to alter the polarization state of light. Here's a detailed explanation of how it works. 1. Basic principle. A quarter wave plate is made from a birefringent material, which has different refractive indices for light polarized along different axes. When linearly polarized light passes through the quarter wave plate, it is split into two orthogonal components, the ordinary ray, O ray, and the extraordinary ray, E ray. These components travel at different speeds due to the differing refractive indices. 2. Phase shift. The key function of a quarter wave plate is to introduce a phase shift of 90 degrees, or a quarter wavelength, between the O ray and the E ray. This phase shift is achieved by carefully choosing the thickness of the plate so that the optical path difference between the two rays is exactly 1/4 of the wavelength of the light. 3. Conversion of polarization states linear to circular polarization. When linearly polarized light enters the quarter wave plate at a 45-degree angle to the optic axis, it is split into two equal components. The phase shift introduced by the plate causes these components to combine into circularly polarized light upon exiting the plate. Circular to linear polarization. Conversely, if circularly polarized light enters the quarter wave plate, the phase shift converts it back into linearly polarized light. 4. Mathematical description. If the incident light has an electric field vector \math E that can be decomposed into components E_x and E_y along the principal axis of the birefringent material, the quarter wave plate introduces a phase shift \delta equals \frac pi2 between these components. The resulting electric field after passing through the plate can be described as E equals x caret plus it caret. For a quarter wave plate, \delta equals \frac pi2, so the components combine to form circularly polarized light if the initial light was linearly polarized at 45 degrees to the axis. 5. Applications. Quarter wave plates are used in various optical applications, optical communication to convert between different polarization states for signal processing, microscopy to enhance contrast and reveal details in birefringent samples, laser systems to control the polarization state of laser beams for various applications. 6. Practical considerations. The effectiveness of a quarter wave plate depends on the wavelength of the incident light. It is designed for a specific wavelength, and its performance can degrade if used with light of a different wavelength. Additionally, the orientation of the plate relative to the incident light is crucial for achieving the desired polarization transformation. 12. In summary, a quarter wave plate works by introducing a 90-degree phase shift between orthogonal components of polarized light, enabling the conversion between linear and circular polarization states. This makes it a valuable tool in many optical systems and applications. Gauss's law for electricity states that the electric flux through a closed surface is proportional to the charge enclosed by that surface. Mathematically, it is expressed as contour integral SEdA equals 0 kenk, where \math E is the electric field, d\math A is an infinitesimal area on the closed surface, S. Q_text inc is the total charge enclosed within the surface. \epsilon_0 is the permittivity of free space. This law indicates that electric charges produce electric fields, and the total electric flux out of a closed surface is proportional to the enclosed charge. 2. Gauss's law for magnetism. Gauss's law for magnetism states that the net magnetic flux through any closed surface is 0. This implies that magnetic monopoles do not exist. Mathematically, it is expressed as contour integral SBdA equals 0, where \math B is the magnetic field. This law indicates that magnetic field lines are continuous loops with no beginning or end, reflecting the absence of isolated magnetic charges. 3. Faraday's law of induction. Faraday's law of induction states that a changing magnetic field within a closed loop induces an electromotive force, EMF, in the loop. Mathematically, it is expressed as contour integral CEdL equals dT/dB, where \math E is the electric field, d\math L is an infinitesimal element of the loop, C \phi_b is the magnetic flux through the loop. This law shows that a time-varying magnetic field generates an electric field, which can drive currents in a conductor. For Ampere's law, with Maxwell's addition, Ampere's law relates the magnetic field around a closed loop to the electric current passing through the loop. Maxwell added a term to account for changing electric fields, leading to the modified Ampere's law, contour integral CBdL equals 0, in plus 0, where \math B is the magnetic field. d\math L is an infinitesimal element of the loop, C I_text inc is the current enclosed by the loop, \mu_0 is the permeability of free space, \phi_e is the electric flux through the loop. This law indicates that both electric currents and changing electric fields produce magnetic fields. 5. Interconnections and Maxwell's equations. Maxwell's equations unify these laws into a comprehensive framework describing electromagnetism. Gauss's law for electricity describes how electric charges produce electric fields. Gauss's law for magnetism indicates the non-existence of magnetic monopoles. Faraday's law of induction shows how changing magnetic fields induce electric fields. Ampere's law, with Maxwell's addition, describes how electric currents and changing electric fields produce magnetic fields. 6. Electromagnetic waves. The interplay between Faraday's law and Ampere's law, with Maxwell's addition, leads to the propagation of electromagnetic waves. A changing electric field generates a magnetic field, Ampere's law, and a changing magnetic field generates an electric field, Faraday's law. This self-sustaining process allows electromagnetic waves to propagate through space. 7. Practical implications. These laws have profound implications in various fields, electronics and communication. Understanding how electric and magnetic fields interact is crucial for designing circuits, antennas, and communication systems. Power generation. Faraday's law is the principle behind electric generators and transformers. Medical imaging. Techniques like MRI rely on the principles of electromagnetism. In summary, Gauss's law, Faraday's law, and Ampere's law are fundamental components of Maxwell's equations, which describe the behavior of electric and magnetic fields. Their interconnections explain the generation and propagation of electromagnetic waves, forming the basis for much of modern technology. That was all. Goodbye.